Everybody. Part 2. Now, here's the thing. I sketched these up real quick, hoping maybe we would save some time. And I hope you're noticing. Oh, I'm kind of in the way on this one, aren't I? Can I move that down? No. Okay, I guess I'll put me over here. So I hope you're noticing that they don't tell you on all of these what the object is actually doing, okay? This says object is pulled by a force parallel to the surface. Oh, I erased part of this. Oh no. Oh no. I'm going to have to redraw that. It just says pulled by a force. It doesn't say what the object is actually doing. It just says it's pulled by a force. I showed that it's moving with a constant velocity, which means that my force diagram has to be balanced if I'm saying there's no acceleration. Number 12, this just says that the object is pulled by a force at an angle. I decided this one was unbalanced. And it was going to accelerate. You may not have. I don't know. I don't know what you decided because it doesn't tell you. Now this one, 13, it does say the object is pulled upward at constant speed. So this does say constant speed. So it has to be constant, no acceleration, has to be balanced. Has to be. Number 14, again, object is pushed by a force applied downward at an angle. Now, I assumed that it was a person pushing, but I said that it was balanced in this case, moving with a constant velocity, no acceleration. Now, here's the thing about these. Not all these are right. I got to get myself out of the way. Not all of these are right. Okay? Based on my interpretation, I should say, based on my interpretation and the motion map that I created, not all of my force diagrams are correct. So I think I want you to just think about that. Think about that. The fact that, let me fix this motion map. That's bothering me. Oh gosh, now I gotta get my pen back. Oh, this was supposed to save time. Okay. So, if I'm saying that the first one, the object pulled by a force parallel to the surface, if I'm saying that this is balanced, is my force diagram correct? If I'm saying that this is unbalanced and I'm accelerating, is this force diagram correct? For 13, balanced, it says up. Is this force diagram correct? For balanced, upward moving in a constant velocity. And lastly, number 14 here, I'm saying that this is balanced, constant velocity, no acceleration. Does this diagram show balance? Now, maybe you should pause the video at this point, and then think about it, and then come back, and then I'm going to start the explanation here in a second. So let me get myself out of the way again. All right, so pause it again. Think about it. I want you to look at these with some detail and think, okay, is this showing balance? Is this showing unbalance or an imbalance? Okay, the discussion. This one here. This one, to me, is showing an unbalanced force to the right. This is not balanced. This diagram is not balanced. I'm saying it's supposed to be balanced. So what am I missing? Something has to be here. I need something else in my diagram here to create balance. What do you think that would be? There's got to be something pulling opposite the direction of the string to create balance with the string, the force of the string. What could it be? What could an object pulled across a floor, what force could there be that would balance out the force of the string on the block? I hope you're thinking friction force, and it would be a kinetic friction force. So really, for this diagram, oh no. Every time I touch my window to move my face around, oh no. This thing has not been cooperating today at all. There should be a force of friction here on block. Now again, friction is not technically the agent. The surface, the floor is the agent. So it's the force of floor's friction on the block. That now is balanced. Up and down were balanced. Right and left were balanced. I suppose I could use two congruent marks on each side there to show that those are supposed to be the same size. That now is balanced. If you said that the object being pulled was accelerating and you had a motion map that was showing an imbalance with an acceleration to the right, then the way I had drawn it first, that'd be correct. So if that's the way you interpreted it, then your force diagram is right. And here's the thing. If they don't tell you what's happening and they just say something's being pulled, but they don't tell you if it's moving or not, or how it's moving if it is moving, then you have to just, I guess, decide that on your own. Now, also in this case, if you said it was at rest, I don't know if anybody said it was not moving at all, because there's no motion lines here. It doesn't say that it's even moving, period. Then it would be the same as this. You would have no acceleration, dots instead of dots and arrows, no movement, balance, and it would have to be balanced still, meaning the string can't pull any harder than the force of friction is pulling. Balance. All right, now, that's number 11. Number 12 I said was unbalanced. Now, you may not have. Since I said it was unbalanced, what do you think would be the case here? Does this look like it should work for this? Now notice my gravity force is big. The force of table on the block seems kind of small. Like, is this even going to work? Will this produce an acceleration horizontal parallel to the floor or the table, it says? It's a good question. If I start moving these around though, if I move this one down here, tip to tail, ooh. Oh, come on now. Move that down there. Move this down here. Oh, look at that. Look at that. What is that going to produce? That is going to produce a resultant vector that looks like what? That resultant of those three vectors added together produces an imbalance to the right, which is the direction that I'm saying it's accelerating. So that diagram right there, that works. That produces an acceleration horizontal to the table. Parallel to the table, horizontal, in the direction that my motion map is showing an acceleration. That works. And isn't it curious that the only way that can happen, if the force of table is too big in this diagram, if it's as big as the gravity force, that'll never work. That force would end up sticking up way up here like this. And that would mean that your acceleration would be up at an angle, and it isn't. This thing's going to slide across the floor. So that means that the force of the table has to be acting less than the force of gravity. Interesting. So let's put that back here. Let's put this back here. Now, if you said that it was moving with a constant velocity in your motion map, then you have to show balance here. Well, how would you show balance in this diagram? How would you get this diagram balanced? Because right now it's showing imbalance to the right, which means we would need something pulling to the left to make it balanced. Yeah? Something pulling to the left to make it balanced. What could possibly be pulling to the left on this block as it's being pulled to the right by the string? The friction force, maybe? There could be a friction force here. If you said it was constant velocity or it wasn't moving at all, then there has to be a friction force here. Now what happens? What happens if I start moving all these around? Move this over here, move this one over here, move this one over here. Oh, wait. What's happening here? Oh, I didn't move this one yet. Move this one up here. Yeah, no, why did I move that down there? And then move this one up here. Oh, the gravity one's got the dot. Hold on. I should have moved them all. I should have kept gravity in place. All right, I'm going to do it like this. I'm going to tip to tail down here, tip to tail right here, and then tip to tail right here. Oh, look at that. And what does that do? That gets you right back to the dot. All four of those vectors, when you add them together, tip to tail, they create balance. They get you back to where you started, meaning they cancel. They cancel each other out. They sum to zero. There's no imbalance. If the blue one is the friction force, that's the only way you can create balance with that diagram. I hope you're seeing that. I hope that's making sense. All right, moving on. 13. Now, this says balanced, no acceleration, and I have force of gravity down, force of string up. Some people want to put a force of pulley in here, but is the pulley in contact with the block? No, only the string. The string's in contact with the pulley, but only the string's in contact with the block, not the pulley. So that is going to look like this. There's no other option. There's nothing else that could be in there. And people do not like this. The fact that that thing is going up, but there's no imbalance making it go up, that people don't like that typically. Because it's one thing for something to roll across the table or slide somewhere and say that it's balanced. It's another thing to say something's going up and say that it's balanced. But it is. And if you were in the room here, I would show you I have a little demonstration I would do, and maybe I'll do that when we come back next week, that would kind of reinforce this and show you that if you have equal forces up and down on that once you set it into motion, it will just keep going very smoothly, just like the dry ice sliding across the table. The same would be true here. If you can eliminate all of the friction in the pulley, that's the caveat there. There can't be any friction forces in the pulley. All right, 14. This object is pushed by a force applied downward and at an angle. Now this shows balance. I've said that it's balanced. Is my force diagram showing balance? Hopefully you thought about that earlier. If I start moving these around tip to tail, this one goes down here, this one goes right here, that's not balanced. In fact, we have the same kind of situation going on here. That's showing, oh, look at that, that's almost exactly the same size as the one above. That's showing that we have an imbalance. When you add the gravity vector plus the force of the person on the block plus the force of the floor on the block, if you add those three together, you end up over here on the left side of the dot, which means we have an imbalance. Not balanced here. I said it was balanced in my diagram, in my motion map, but it isn't. Not the way I've drawn the force diagram. So either I have to change my motion map to reflect what's happening with my force diagram, and so I would have to show what? An acceleration. I would have to show an acceleration in my motion map to the left here, to the negative direction. to match what this motion map or what this force diagram says, or I'm going to need another force in my diagram to get me back around to the dot. I would need a force like the blue vector to the right. Well, what possible force could there be to the right to make me balanced in this situation? What could there be that's pulling to the right over here? So if I put all these back where they were supposed to be, what could be pulling on the block to the right? I hope you're thinking that there could be a friction force between the floor and the block. There could be a friction force here between the floor and the block that would be pulling to the right here, so that when these do get moved around tip to tail, and I'll move them in a different arrangement this time, or no. I'll move, let's see, I'll go this one here. How about that? This one here. And then this one here. Boom. How about that? How about that? Gets me right back to the dot. Now, I want you to notice here, the only way to get me balanced back to the dot is if the force of the floor, notice the force of the floor has to be bigger than the force of gravity. Has to be. The floor has to be pushing on the block more than gravity is pulling down on the block. And why is that? Well, think about this. What is happening? What is happening in this scenario? This person is pushing the block, not just horizontally, but also vertically. Like when you push down at an angle like this, some of the force you're pushing is going down, some of it's going horizontal. And so because of that, the floor is pushing up, not just against the force of gravity on the block, it's also pushing up against the person that's pushing down at an angle. I don't know if this is confusing or if this is making sense, but when you move these things around, when you move these four vectors around, so they're all tip to tail to each other, they will balance. So the way I had originally drawn it did not agree with my motion map. My force diagram was showing an imbalance, even though I said it was supposed to be balanced. So you have to make sure on these, as you do these, that if it's balanced, you better have a balanced force diagram. If there's an imbalance in your motion map and you have an acceleration, then you better have an imbalance in your force diagram. They have to match. Hope that makes sense. Now, for 15 and 16, forget about 17 and 18. For 15 and 16, I guess we could do that real quick. The object falling, no air resistance. So notice the motion lines here. That to me says that it's getting faster as it goes down. Getting faster as it falls. That's an A in the downward direction. Now, what forces are acting on the block at this point? There's only one. The gravity force is it. There is only a gravity force. So does the force diagram show an imbalance? Yeah, because there's only one force there. It's gravity down. That's it. End of story. 16 here. This says it's falling at a constant or terminal velocity. Now, terminal velocity is a term used for objects that are free falling. Does anyone know what's terminated? What gets terminated when you reach terminal velocity? I want you to look at the motion here. It's showing you motion lines that are equally spaced, which means this block is now traveling how? So if I draw a motion map here, this block is falling at this point with a constant velocity. What about that block's motion has been terminated? It doesn't have acceleration anymore. Here it's accelerating, but now it's not, which means there has to be something else acting on the block. Do we still have the gravity force? Of course, we have to have the gravity force. I didn't say on block over here. but we have to have something else. There has to be something else, and they have to be equal amounts, or we can't have balance. So what could possibly be acting on this block for it to reach terminal velocity and have its acceleration? Again, I would say there's a force of air on block. Now, some people might call it air resistance. I don't care what you call it. The only thing in that picture that could be acting on that block is air. We apparently ignored it over here, or maybe it's just moving really slowly and the air's not having much of an impact. But the faster this thing goes, the more force of air resistance you will get until these balance. And when those two forces balance, when the force of air on the block equals the amount of force that gravity is pulling on the block with, then you will no longer have acceleration. We achieve balance, and then the object will continue to fall at a constant velocity the rest of the way. Now, if you got a parachute on, your terminal velocity is going to be kind of slow, hopefully. If you don't have a parachute on, then your terminal velocity is going to be pretty fast. So how fast you can fall is going to be determined by how much force of air resistance you're able to create quickly. The faster you can create that air resistance force, like with a big old parachute, then your force of air resistance and your force of gravity can balance out at a very slow speed. If you don't have a parachute, you're going to be moving pretty fast. You got to be going pretty fast to make the air resistance force on you as big as the gravity force on you. So again, hopefully this has to be a shorter video than the last one. But anyway, hey, that's this whole thing. Make sure you get all this watched. Obviously, if you made it to this point, you did watch the whole thing. Anyway, we'll pick back up. There's going to be obviously a worksheet 2. This is worksheet 1. There's going to be a worksheet 2. We'll get to that next time. So take care.